So we have the following easy lemma. The zero ideal of a ring. Well, every ideal is in a ring, so I will not write this. The zero ideal is maximal if and only if the ring, so now we need to write it, if the ring R is a field. Proof. Well, let's think about it. There's only one direction we need to prove, because a field, as we know, has just the zero ideal if we talk about proper ideals, so not counting the ring R itself. So of course, zero being the only ideal, the zero ideal is also maximal if R is a field. So there's nothing to prove in the direction if R is a field, then zero of course is a maximal ideal. So what we need to prove is that the zero ideal being maximal implies that R is a field. So suppose zero ideal is maximal. Well, if the zero ideal is maximal, let's pick an element A in R and look at the following ideal. A times R. So this is the ideal you get by multiplying A times all the elements in R. This is of course an ideal, but since the zero ideal is maximal, this ideal has to be R. So depending on your terminology, this is not really an ideal. I mean, depending on if you call R an ideal, or if you only or if you prefer to call ideals only those ideals which are proper ideals. So anyway, R times A, A times R is R, and this means that there exists a B in R such that A times B is 1, because after all 1 is in R, and this statement here, A times R is equal to R, implies that there is a way to write 1, and this is precisely what we get by multiplying B to A. So A times B is 1, and this means that we can invert A. So A is in the multiplicative group of R, which we denote by R star. So this is the group of elements of R that have multiplicative inverse. And now note that A was arbitrary. And this means that every A in R has an inverse. So this precisely means that R is a field. And we're done.